So good morning, ladies and gentlemen. Thanks for being here today. I hope you guys all were able to attend the awards last night and see everyone receive their wonderful concrete awards. I'm a big fan of that because I've been trying for 11 years to get them to make them out of concrete. So we had success there. If you did miss the awards show, though, we encourage you to visit the project videos available on the website. That's aciexcellence.com. And as Denisha said, we're fortunate today to have 10 of the project winners joining us here for this 2-hour session. To accommodate this, each presentation is going to be about 10 minutes. So Denisha's got a big hook. If you talk too long, we're going to grab you and pull you off. If time allows, you'll have the opportunity to ask a few questions. Please step up to the microphone there in the center of the room so we can all hear you. But let's go ahead and get started. Our first presentation is from John Gwynn, who's the owner and chief science officer for Roman Cement, and David Hall, chief executive officer. John is an ACI member and active on ACI Committee 211 on proportioning concrete mixtures. He has over 30 years of experience as a patent attorney and innovator, and holds more than 40 patents related to Roman Cement's low-carbon cement concrete mixes, and has led numerous field tests and collaborations to advance sustainable concrete technologies. David brings over 30 years of entrepreneurial and executive experience, having founded and led several successful companies across technology, health, and financial sectors. His leadership continues to drive Roman Cement's mission of combining innovation with practical sustainability. They're going to present on the flatwork category first place winner. This is the low carbon concrete bus charging station. And the presentation is titled Using Mineral Fines to Reduce Cement Without Compromising Quality. Please welcome John and Dave. Yes.
Can I click it this way too?
Correct.
Okay.
Yep, laser pointer at the top.
Okay, first of all, after seeing all of the attendees and the winners last night, and myself, I mean, the scope of the building project was so amazing. Ours is very simple in comparison, so I have to congratulate the people that built massive structures and reconfigured buildings and very physical and other things. But I want to say that what we're presenting is very simple, but it is the culmination of a lot of work. And we have started off with the technology at particle size, select a ternary blended cement, and in our ideal cement we would have, in a broad distribution of particles, we would have cement within a certain zone. We would have a very ultrafine pozzolanic material that's very reactive, and a coarse mineral filler, and a carotid and size distribution. What we did with concrete was just the materials that we could find off the shelf, but we didn't have to specially process, so we could just implement this at the concrete level. Anyway, we were able to redesign several mixes of ready-mix companies in California and in Utah, and we were able to, from the materials cost standpoint, reduce the cost of $5 to $12 per yard. We were able to improve the quality of concrete. We don't try to increase the strength, we try to match the strength, but we did some durability tests, and they came out very good, and the workability is very good. Even though we call ours a low-carbon concrete, because of the way in which we use a mineral filler, we're able to maintain very good workability. So everybody knows this. Okay. Yeah, sorry. Okay, so everybody knows that, typical concrete always has a cement and one or more supplementary cementitious materials. And, of course, the point is to create better concrete, to react with the cement, and to, make a greener and more sustainable product. And if designed right, you get very, very good concrete using those materials. Like I said, we've always looked at a ternary blended material. Ideally, the cement and the SCM and the mineral fines wouldn't have the same particle sizes, but in this case, the SCM we used was fly ash in this project, had about the same particle size as the cement, and then our mineral fines were a coarse limestone powder that we found off the shelf. But we were able to use it to reduce cement content significantly and make what we believe would qualify as a low carbon material under 323, but we didn't have the workability issues that you might have if you reduced cement paste dramatically. Anyway, as we know, typical supplementary cementitious materials like pozzolans and fly ash and slag will have a strength retarding effect. They ultimately yield great strength, but early on they kind of have a
retarding effect, but by using this coarse limestone powder, it has an accelerating effect, and so they kind of offset, and we get very good results. We can reduce the cement content further from a binary blend by 20 to 30% and get good strength, same or better strength, good durability and workability. And pumpability is a key factor, and so one of the things we had to do was a flat work, and we had to have good pumpability. And so anyway, here I'm going to get into the mix that we redesigned. Again, this is just an impressionistic version of our idealized cement material. But, sorry, just trying to look at this. Sorry about it. Okay, so this here would be the mix design. This is the city prescribed mix design: 489 pounds of cement per cubic yard, 122 pounds of fly ash per cubic yard. And we reduced the cement by 20%, nearly 100 pounds per cubic yard, reduced the fly ash by 15%. And so the total cementitious went from 611 pounds per cubic yard to 495 pounds per cubic yard. And then we replaced that with 150 pounds of pulverized limestone, which still was quite a bit less expensive than both the cement and the fly ash, and so ultimately the cost went way down, even though we had to use a little bit more admixture to get the right flow. But we had a target air content of 6.3%, and the slump had to be about 5 inches. We did this project. It was for the rechargeable bus station, and we found that it pumped well. It seemed to behave exactly like the concrete that everybody's used to. It finished well. There's the aerial view of how the bus station ended up looking. Here is a letter of commendation from the contractor who did this, and they liked the fact that the concrete met or exceeded their expectations in terms of workability and how it flowed. This is kind of a summary, but the company who pumped it said that the pressure required to pump the concrete went down by about 20%. There is a statement here that says that the average strength from a 4,000 PSI air and train mix was 5,450 right here, but one of the trucks was actually, one of the trucks was actually 6,200. This is an average. There was, they took some material, and anyway, it's hard to go through it, but they actually added a little bit more water at the end after doing the air test, and they got lower results. So this is just the average, but it was a poor average. But they said that that it performed well, it finished well. Anyway, they thought it was a very good project for them, and they enjoyed working with it. Ultimately, we did some durability testing later on because that's not something we did beforehand, and we took a typical concrete mix of the same strength, 4,000 PSI, used a reactive aggregate to do the ASR test, and simply by reducing the cement by 20% and adding limestone powder with no special additives, we were able to reduce the alkali silica reactivity by 30%. Resistance to scaling was dramatically improved. Theoretically, it's because our cement paste matrix was less porous because we have a higher particle-packed cement system with the limestone powder. Rapid chloride permeability test, we improved that. The surface resistivity went up. Freeze-thaw was about the same. And then we had improved compressive and flexural strength compared to the control mix. And anyway, some of our partners we want to thank. The City of Salt Lake City is who funded the project for the bus stop. UTA was, that's the Utah Transit Authority. It's for a rechargeable bus station. Geneva Rock was our concrete producer. Stacy and Whitbeck was the general contractor. CMT was our engineering firm who did a lot of our testing before we poured. And Altiview helped us do the durability testing. So that's all I have, and I was curious if anybody has any questions.
Any questions for John? Director?
I probably should know this, but 1797 materials that you use was filler, right? Is that part of this water cementitious ratio calculation that allows ACI 318 allows, or is it like a, considered as an inert filler?
You mean the limestone filler? Yeah, so, it qualifies under ASTM 1797, which is limestone refractory aggregate, tunnel fillers, and also ACI 211, which is N now. So, it's not a traditional supplemental cementitious material, it's limited in the
Okay, yeah, so that's what I thought. The main issue we see is a lot of specs have this water cementitious ratio requirement, so that'll be a challenge, right? Otherwise, it's great. For a performance spec, this is a great
That is like one of the best questions you could ask, because we're trying to get approved by the Department of Transportation. They say, well, we have a limit of water cement ratio of 0.44, and you can't exceed that. And of course, when we did ours, the numbers aren't up there, because we began with about 4.43, 0.44 water cement ratio, and by reducing the cement by 20% and fly ash by 18%, we didn't reduce the water by that much, maybe by 85% or something like that. Then putting in the limestone powder, the water cement ratio would have gone up to say 0.5 up. The water to powder ratio, putting the limestone went down about 0.4 up. So we have this kind of straddle where, from the water cement ratio standpoint, we should get weaker, but because we have more powder, it makes up for the strength, and it also creates a more part of the pack system. So it ends up working out well.
Very good. In the interest of time, we'll continue on. Thank you, John and David, for showing us how to make the world a better place with some of these materials. So our next presentation is from Adam Thompson. Adam is General Manager and Vice President of Northern California for Trademark Concrete Systems. Adam is going to share insights on decorative concrete category's first place winner last night, the California Firefighters Memorial, in his presentation, Honoring Service in Concrete. Please join me in welcoming Mr. Thompson. And you can see the screen from here.
Yeah, thank you. Is this the clicker?
Yeah, of course. You got it.
Perfect.
Cool.
All right. Nestled in the beautiful grounds at Capitol Park in Sacramento is the California Firefighters Memorial. My name is Adam Thompson with Trademark Concrete, and we had the distinct honor of building this memorial and doing all the decorative concrete work. The original memorial was built in 2002 with the first ceremony in October honoring fallen firefighters in 2003. The intent of this expansion, which is phase one of the expansion, there'll be phase two later, was to add a series of axe walls to allow for more names to be put on as individuals pass. The process was very involved from the beginning, very collaborative. I want to thank our partners. Turner Construction was the general contractor. Lionakis was the design firm. And a special thank you to Don Romo, who is the artist on the project from Romo Studios. So we got involved early making samples. Here are a few examples of some 6x6s. Don had brought in some bronze statues. There's bronze throughout the Capitol Park. And we were looking to find colors and finishes that kind of fit his vision. And through the design process, we actually got to use some VR goggles, walk through the memorial and see different heights and elevations of the statues, of the accent walls. So it was a very hands-on collaborative process. We used a blended mix design, pumpable through 3-inch line if needed. We were limited with some access issues at the grounds there. Probably the biggest hurdle as it came to concrete was the temperature. So 110 degrees in Sacramento in the middle of the summertime. So we just worked with Cemex, the ready mix provider, and we were able to get concrete at 5 a.m. every day just to make sure that we could control our pours. Here's an example of our shop drawing. The red lines outlined there are the construction joints. The original design for this project was actually to be bluestone pavers for the flat work. So the artist and the design team wanted to keep that concept, but do it in concrete. So we actually put together a plan to give them that running bond look. These are 3 foot by 5 foot. And so everything was formed in a 3-foot bay. The blue lines are the saw cut control joints. So we had a 3/16 saw cut control joint, just isolation joints at the vertical structures. There were benches, sign walls that had template sandblasting. You'll see in some photos that are upcoming. Here was how we poured it. So you can see the control joint versus the construction joint. Centered in there is a bronze inlay that is 8 foot in diameter. So we kind of softened the coastline a little bit there to prevent cracking. Poured it in 3-foot wide lanes in the running bond pattern and used a color hardener for the final color. The grounds before the expansion and a little aerial shot of where it sits within Sacramento with the Capitol in the backdrop. Here's in progress. You can see the formwork in place. All the vertical work, the foundations for it, the axe walls were substructured with concrete. The circular pedestal there will, in the future, in the next phase, we'll have a statue placed there. In addition to the 8-foot diameter California inlay, there was 2 bronze medallions at each end. You can see in the front picture there that were poured in place. There's kind of from paper to completion. So there's our shop drawing on the left, and then an aerial shot featuring the axe walls at the center. The geometry of everything on this was tricky. The layout was complicated. All of the pieces in the center there are granite. And then you've got granite meeting limestone, meeting poured in place concrete with a lot of different geometry, radiused edges, etc. The Maltese cross is inlay in the granite. Decorative concrete going through the center wall there with the inset lighting that lights it up in the evening time. I'll show you a nighttime photo here in a moment. Front entry wall there to the left is poured in place with a sand finish, template sandblast lettering, bronze medallion in the front, 4-foot diameter on that, and then obviously beautiful statue bronze work and stone work. Gentleman featured there is Dale Turner. He is the project manager for the California Firefighters Foundation. They raised all the money in-house, privately funded, to create this expansion, and he did a great job of bringing the artist's vision and the spirit of what it is to be a firefighter and what the memorial wanted to represent, as he was a firefighter. To the left there, that's a bench, again, with a slight reveal at the bottom, template sandblast, etching, sand finish. That's after completion, aerial view. The axe walls lit up at night. The center wall remained throughout the course of the project. That's the original wall. It remained protected. That has the names of I believe it was 980 fallen firefighters. These axe walls will then feature new names. And that's the end of the presentation. This was one of the most meaningful projects that I've been a part of. So it was a great opportunity to utilize our decorative concrete expertise and partner with great people for a great cause. And we're honored to win this award and to represent the California Firefighters Memorial. Thank you.
Any questions for Adam? I have one quick one. The attachment for the bronze sculptures?
Yes.
Is that cast in, or was that drilled in epoxy?
The one with the jacket, that's in the limestone. Yes,
Oh, okay.
Yes, drilled in the limestone.
Yep, very good, very good. All right. Excellent project. Thank you for your presentation. All right, our third presentation from a familiar face, Jose Izquierdo Encarcion, President of Porticus CSP, and Pablo Quinones Cordero, AIA NCARB, Principal Architect and Founder of PQC Architectural Studio, LLC in San Juan, Puerto Rico. Jose is the ACI past president, ACI honorary member, and chair and voting member of multiple committees. Pablo is an award-winning architect with over 35 years of experience specializing in historic preservation and resilient design, including leading the restoration of this project and other Puerto Rican landmarks such as the Capitol Dome and La Fortaleza Palacio de Santa Catalina. Together, they're going to present the repair and restoration category first place winner, and also, if you attended, the overall winner, congratulations, the Puerto Rico Capitol Dome project with their presentation, Repair and Restoration of Puerto Rico Capitol Dome Buildings. Please welcome Pablo and Jose to speak about the project. Take her here, looking back, and then there, and if you can step around so they can hear. Thank you.
Let me impressed you knew how to pronounce my last name, Quinones. Good morning. Just to give you a background, I'm just going to concentrate in three major elements because the technical person is right there, Mr. Izquierdo, and he'll give you the nitty-gritty. But this is the real estate of the capital, and I want to make you aware this is a very severe tropical coastal zone. That means corrosion supreme. Not only the building is from 1929, it was conceived and designed for cross ventilation. So as the windows were open, guess what? All this salty air was going into the building. So we do have what I call a steel or standing concrete ship with the Atlantic Ocean to the north and the Bay of San Juan to the south. So that gives you more or less a background of how severe the environmental conditions can be. In my opinion, historic buildings are sort of different from constructions. And I have told the superintendent of the Capitol, I'd rather do the building from the roof down than building, which is from the foundation up. Why? Because humidity or moisture is the biggest damage to historical buildings. So I'm going to give you a little historical background. And the Capitol building is the result of a competition from 1907. So actually, Frank Perkins, architect Frank Perkins from New York, to give you a perspective, was the one that won the competition for the Capitol building. But being in Puerto Rico, and we're always controversial, the building didn't happen with Frank Perkins' design. Only the foundation was done with Frank Perkins' design. From 1920s, imagine from 1907, which the design competition happened, only in the 1920s was that the actual construction of the foundations happened. In 1921, they stopped the construction, and they did a second design, or third design. Architect Rafael Carmuega. Happens to be that Frank Perkins was from New York, and Rafael Carmuega was a Cornell graduate from the US as an architect. So the Capitol building, when you look at it, it's inspired in the Law Library from Columbia University. And if you look at the Law Library, it looks pretty similar in concept, in massing and concept. So the structure, to be short, is a reinforced concrete structure cladded in Georgia white marble and a collection of very intricate ornamental terracottas. So the Capitol Central space, which is an atrium, also is open. So this is the project story. So we go location, background, and this is the story. In 1998, after Hurricane Georges, which was not a big deal in Puerto Rico, but a lot of water, caused these conditions here that you can see. And just by plain observation, which I call observation, we knew there were some problems happening in here. So we alerted, I want to make you aware that the Capitol is managed by the superintendency of the Capitol, which is designated by the legislature, and blah, blah, blah. In other words, bureaucracy, okay? So in other words, decision-making and processing is not the most efficient or fast. So we told in 1998 we need to get a subject matter expert. We did get, at that time, Smithsonian Institute conservators in the person of Joe Sembert and Martin Weaver, which were very recognized at that time. And they did for us, after 2 years of me convincing the superintendency, we did a study, which was later on published in the, how do I go forward? In the Traditional Building magazine. We tried to preserve that southwest corner, but we ended up deciding that it was best to dismantle the corner to understand what was going inside the corners of the building. So this is the first time I've ever heard of Syntec, which you see some sketches here. We spent about 4 hours doing sketches of how to preserve the 7 cores of terracottas so that we could, at the same time, understand how to reattach them, okay? If we dismantled the corner, it was not that hard to put back, but we were trying not to dismantle the entire cornice with the base of the Capitol. So that was some time that we spent. And again, like I said, it took us like 5 or 6 years to get another project to get back in track. At the same time, I had convinced the superintendency, let's go ahead and do the molds for the terracotta pieces. To give you an idea, There are 7 courses of terracotta and 1,568 pieces overall around the base of the Capitol Dome. That's how complex this thing can be. So when we started doing this project, we understood that, one more time, we had sort of a crisis because the other areas, you started seeing some modillions that were falling at the same time. So we even made the newspaper, you know, the building that says there, se cae en pedazos, which means the building is falling apart. And then el tiempo le pasa el tiempo, so I mean, time is passing, you know, on the building and making it worse. At the same time, at the main entrances, we were seeing some collapses and so forth. So we were trying to make this, instead of historical preservation, hysterical preservation, to get the message through. So finally, we go all the way to 2022, and we got called by the superintendency because they were trying to do a restoration of the mosaics in the atrium. And I told the superintendent, you can't do that unless you do the dome, first of all, because it's the highest point in the Capitol building, and you need to address it. Being architects for superintendencies in 1985 or 86, we had 30-plus years of collecting, because I took it as a passion or a mission to collect every single drawing I could of the capital of Puerto Rico, and this proved to be essential for our project. I even got the original structural design of the Capitol. It's a 1924 drawing, hand-drawn, and these sections that you see there are also the original drawings. And these photographs show that in 1929, this is the era, more or less, where the dome was being built. So these photographs were all instrumental in us understanding what we were dealing with, in essence. So in other words, now we have the project. So that what we do, thanks to the digital drawings, all our terracotta pieces and so forth were sort of like a Lego puzzle. And we organized each one of them in a specific code. And Gladden McBean, which we convinced the superintendency to purchase the terracottas in advance, because terracottas will take anywhere from 4 to 8 months just to get them from original intention of building the terracotta to actually getting the material on site. So we purchased the terracottas ahead of time when we finally decided to go ahead and bid the project. So what happens after we get all these drawings and we get all this stuff? We went into the bidding process, and we were fortunate, what I call myself a double whammy, because we got a contractor that happened to be a structural engineer also. So we had Izquierdo, and then we had the contractor, Jose Gaya, from BPMT, who was the contractor, and we were able to, as you can see, this is the process, I'm trying to abbreviate as much as I can, a very complex process of the corners could be easily installed, but then the other pieces were done in Syntec, and then Izquierdo will be more in detail with this. As you can see, the pieces had to be hand-colored. Edison Coatings was the supplier for some of the finishes for the terracottas and so forth. And here we are seeing the results of the final project there. And we were able to preserve the interior, which is the mosaics.
Well, the architect always fix more. We're done. Let's try to do this in 2 minutes. A recognition to the scaffolding guys. They did a fantastic job. All the exterior scaffolding is curved. The interior between the two domes is curved, and it was essential for the performance of the contractor. This gives you a section of the original construction plans, which we were able to review and verify of the rebars. You can see that there are two domes. Both of the domes are made out of concrete. The one who caused us trouble was the exterior dome. We don't have time to try to explain the complexity of the structural system. The inner dome is not supported directly into columns down there. It's supported between beams and circular beams and other columns, but we don't have time to go in deeply. We did what is very important, according to ACI Code 562, you need to do testing everywhere. And it was a great lab, spec engineers, they did all kind of testing. And the important one was this. we found that there was extensive honeycombing in the exterior dome from the 1926. We think that because they were afraid of the big angles of the dome, they used a very dry mix, and because of that, this is ACI only existed for 15 years when this was done. So, and the code was 16 pages, published in 1910. This was a big problem. If we have to repair it from the outside, we have to take the marble. The project would have gone nowhere. So thanks to the support of master builders at that time, now Sika, they recommended a micro cement to inject from the inside. It's a micro cement used to stabilize tunnels inside mines. So a process to the diagram on the right, we injected every 16 inches in circles from the bottom up, always from the bottom up. Low pressure injection, only 30 psi. We just want to fill out the voids, and the contractor has to watch that there will be no micro cement on the outside to damage the marble. It happened, I think, 5 times that the micro injection went outside. The basis of corrosion was to horizontal surfaces between the dome construction, salt water, like Pablo said, deposit there. Every time it rains, the salt water goes inside the structure, and that's why they were using regular techniques. They're very important to detailing the drawings, photos of the damaged beam, repaired beam, and then the terracottas was much larger the damage. This shows you the process of the syntax. This is a very important European technology that the rod is inserted into a good attachment area, it's solid, and then it goes in with how you call like a sock, and after then you inject a grout, so it grows and then makes everything together without causing extra stress. Then you tighten the rod and everything stays in place. The contractor make a redesign after we see the extensive damage. This is on the corners. We needed to do some structural extra. We use stainless steel angles and concrete beams, and it was injected. And I wanted to show these 2 pictures. At the end, artists with a small spatula finished the project, because to make sure that all the ornamental terracotta mix. And we received an award from the architects in Puerto Rico, and we're very humble of the ACI award. Thank you.
Any questions for Jose or Pablo? Excellent presentation. Well done. Congratulations again. All right, our next project we're going to welcome Tracy Lowe, International ICF Specialist with Intraspec. Tracy provided ICF technical and architectural support for the low-rise structure category first place winner, the Altamura residence. He will share how this project achieved a net zero disaster-resistant structure in the presentation. Please welcome Mr. Lowe.
I'm probably just going to do the arrow up and down. Okay.
Sounds good.
Again, my name is Tracy Lowe. I was invited here by the actual architect for the project that's pictured here. His name's Nicholas Nikiforuk. He's been working in ICF for 35 years. And he invited me to come because I live in Columbia. We've been talking about ICF for a decade. Unfortunately, Nicholas had to go in for surgery on Thursday and was unable to attend. So he asked me to come in and kind of get his back. So I just got the information on this yesterday. So hopefully I can work through it. And if I can't answer any of your questions, I can give you Nicholas's contact information, and I'm sure he'll be happy to work through it. I do have some knowledge in the industry, so maybe I can answer it, but if I can't, I would be glad to give you some information. ICF stands for Insulated Concrete Forms. It's basically a piece of styrofoam, a bracket, and another piece of styrofoam that build the wall. You pour concrete in it, and you end up with a wall and roofs. And now you have a complete, what we call cave above ground. So the temperature is always sustainable to the same, doesn't fluctuate much, 4 or 5 degrees, and it makes it a really, won't burn down, won't blow away, storms can't interfere with it. And with some new technology we're coming out in 2026, it's even going to be better. So that's basically the gist of it. This is a front view of the property that was finished with the all concrete and the concrete light pillars there. Another view of the unit with the steps. This is the rear view of the unit. This is the 12-foot wide footings using the ICF forms. The next 3 slides show all of the footings that are being built so they can pour the concrete. And this is actually them pouring the concrete and getting it ready to dry. So there's all the footings. This is the first floor row of footings that were done. This is the placement of the first row of the ICF forms. Again, there's the styrofoam, the brackets that connect them together, and the other piece of styrofoam. And then those black brackets actually are the studs in the wall to mount whatever you want to mount to it, drywall, whatever it might be. So when the wall is finished, you're done. There's no wrapping, there's no insulation. Put your brick or siding on the outside, put your drywall on the inside, and you're done. It makes this process really, really fast. This is the Altamura family. Nicholas is in the bright yellow shirt on the left there, and then that's the owners of the property. And you can see somebody building another wood project that'll burn down the next time they have a fire. Ours won't. This is the first row of forms going in, sorry. This is, they're putting in the slab rock to fill it, and then they're doing the same there, and then they'll be compacting it as they go along. These are the forms for the light rails or light pillars they made. And there's the actual concrete light pillars right there. The next 4 slides are of the curved wall that they built. This is really cool with ICF. You can actually do curved walls. So here's one, another one with a little sharper curve. And this is the actual pouring of the concrete into the actual wall structure. This is the second floor of ICF walls going up. And then this is the cantilever balcony right there, which is another innovative thing that Nicholas developed. A lot of people that do ICF walls don't do ICF roofs. Nicholas has been doing them for 5 or 10 years now, and he's invented the whole process of getting that concrete roof done at the same time you're doing the walls. So again, at the end of the day, you end up with a cave above ground. And if you've ever been in a cave, it doesn't make any difference what the temperature is outside. If it's 25 degrees, it's 67 degrees in the cave. If it's 100 degrees, it's 67 degrees in the cave. And it's the same thing with an ICF property. This is the ICF roofs. This is the outdoor roofs getting ready to be poured. And the pillars again. And here's them actually pouring the ICF concrete, or the concrete into the ICF roofs. Another shot of them pouring the upper walls and the roof. Here's a drone shot of the completed roof section. Again, getting ready to pour. That's a completed shot of all the wall structures and roofs, all done and poured. This is the rear steps that they did in concrete. There's a beautiful shot with the rainbow above. It's a pot of gold, they called it. This is an innovative little doggy area they built using the curved ICF. That's the finished dog and the side view of that. This is the start of the ICF stairs. Oops. What did I do? I'm sorry, Denise, I hit something. Just popped up.
Oh, don't worry about that. Just, there you go.
Thank you. And then here's the actual steps. And a beautiful shot of the steps with the lights. This is the rainbow, the curved eyebrow they call it. This is the double dormer in the front area. Same thing there. This is a shot of the living room. Living room showing into the kitchen. Pretty nice windows there. Again, the living room, and then the living room into the kitchen. The actual kitchen with the archway. Another shot of that. And then the actual kitchen again with that archway. This is the dining room. Check out that wall mirror. And then the dining room with the lighting. This is the guest bedroom. I could live there. This is the hall bath, guest bath, and the master bath with a walk-in shower. Got to have a gym. And then the music studio. This is the framing of the double-sided fireplace. And then the finished fireplace. And then the double-sided, the master bedroom fireplace. And then the finished fireplace. And this is IntegraSpec's demo they do at all the World of Concrete shows and builder shows that they do. So that's it. Any questions? I'm in the Maryland area. I live in Columbia, and we're actually promoting ICF in this market. It's becoming a more popular way to build houses, especially since people are pushing net zero and want a nice, quiet home. So if you ever need to reach out to me, I'll give you one of my cards, and we can talk about how that might happen. And we are looking for builders and people that want to learn this technology. Thank you so much.
Good. Thank you, Tracy. All right. Our next presenter, Lianjin Bao, Chief Structural Engineer at East China Architectural Design and Research Institute Company, Ltd. He will discuss the structural design and construction of the Chinese fan in the Shanghai Grand Opera House, an architectural landmark inspired by an open fan along the whole. River. The project received honorable mention in the mid-rise structures category for its innovative use of ultra-high performance concrete and bold cantilever design. Mr. Bao will share how his team achieved seamless integration between architecture and structure through creative engineering solutions. Please welcome Mr. Bao.
Good morning, ladies and gentlemen. I'm glad to attend this ACI Concrete Convention on behalf of the team to present the structure design and the construction of the Chinese fan. The Shanghai Grand Opera House is located in the Expo Culture Park. It's the Shanghai Expo 2010 held there. The project is near to the Huangpu River, the Shanghai, China. The architecture design is inspired by an open Chinese fan. It will be one of the most striking project landmarks in China. The total area is 146,000 square meters. The height is 45 meters. The outdoor spiral staircase functions as an accessible rooftop, an observation platform, and a city living room. It is structured topped out in October 2023 and will be open in June 2026. Both spirals rotate clockwise, forming an asymmetric double spiral staircase. The staircase consists of 68 steps. Each step rotates 4.3 degrees and has a height of 410 millimeters. The maximum cantilever length is 32 meters. So the roof is like an unfolding fan. In the accessible area of the roof, the small steps are partially installed, and through the arrangement variation, 136 millimeter high steps and landing platforms are formed. In the non-accessible area, the curtain walls on both sides curve upward to function as inner handrails. The Chinese fan comprises 3 distinct sections. One is the fan pivot, is yellow. As fan surface is green, blue, and the fan head is green. The fan pivot structure comprises a concrete core and 6 shells, and there's a top steel beam. The fan surface is a steel frame structure composed of circular main beams and radial secondary beams. Circular supports are arranged at the edge of the fan surface to ensure the stability of the overall structure. The cantilever length ranges from 9 meters to 15 meters, accounting for the architectural finishes and the ceiling construction. The effective height is only 725 millimeters, so the span to depth ratio is 21:1. The cantilever beams are prefabricated pre-stressed UHPC beams arranged radially and anchored to the concrete shell. Adjacent prefabricated UHPC beams are connected with cast-in-place UHPC joints to form an integrated structure and achieve waterproofing and the durability of outdoor staircase. The UHPC beams are connected flush with the bottom of the concrete 6 shell. The compressive strength of UHPC is 150 megapar, and the tensile strength is 8.5 megapar. The cross section is formed rectangular to a pie shape, minimizing the self-weight. Plus stress is applied to fully utilize the high compressive strength of UHPC. The UHPC cantilever beams are anchored into the concrete shell. Full-scale tests were conducted on 2 UHPC cantilever beams, and the maximum test load reached 1.7 times the design load, and the maximum deflection is about 770 millimeters. This is a test. Uh, 20 cantilever beams were randomly selected for in situ loading test. After the unloading, with no visible cracks or residual deformation observed on the beam. A total of 45 mass dampers were installed. The results showed a significant reduction in vibration by 47%. Through collaborative optimization of design and fabrication, only 2 sets of steel molds were used. A mass production was achieved using conventional concrete precast plants. This is a construction of concrete spiral shells and the installation of UHPC cantilever beams. There's a key construction milestones. The roof is started from July 1st, 2022, and it's topped out on October 21st, 2023. A summary of the construction. Yes, this is some photos during the construction. And the architectural finishes and the decoration was finished. And 2 weeks ago, the Global Engineer Congress was held in Shanghai, and engineers from more than 60 countries visited the project. The key innovation of the project is the seamless integration of architectural design and structural technology, and the structural test, in situ loading test, and the structural health monitoring, validating the safety and the serviceability of the new structure system. And the Shanghai Grand Tower Opera House marks the first application of UHPC technology in large-scale public building in China. And in short, it's a high-performance materials change structure through the engineering, the total design, full life cycle design, low carbon design. At last, I give thanks to the owner and the team, include architectural design, structure design, general contractor, UHPC supply, and so on. Thanks. This is my presentation. Thank you for attention.
Oh, there.
In-place testing. That
The
was,
stairs ended up white, but the concrete was actually gray, so you have to cover it with something, or were they poured in place?
is there application on the HPC to make it white? What was the?
No color.
No color. So that's the.
It was just made from white.
Yeah. This is
finish the up and ceiling down.
Okay, that right. Categories down. Very good, thank you so much. All right. Thank you for that presentation. Our sixth presenter is Satoshi Tatsuno, Senior Structural Engineer with Tasai Corporation in Tokyo. He is going to present on the high-rise structure category first place winner, Satsukika 8.1, the tallest skyscraper in Hokkaido, Japan. This presentation will highlight innovative use of precast concrete for speed, durability, and earthquake resistance. Please welcome Mr. Tatsuno.
Thank you for your introduction. We are very honored that Satsukita 81 has received such a great award. I'm Satoshi Tatsuno of Taisei Corporation. I designed the structure of this building. Thank you for everyone in this project with us, owners, designers, contractors, concrete companies, and more. Now, let's start my presentation. Sapporo, Hokkaido is Satsukita 81 is the tallest building in Hokkaido. This is 48 floors above ground and about 175 meters high. There is a lot of land to build in Hokkaido. However, recently, high-rise buildings with the value of near Sapporo Station are demanded. These are the inside of this building. This is description of concrete usage. In this presentation, I'll explain these technologies that we newly developed and adopted. First, precast construction method with hinge irrigation method. Hokkaido has a lot of snow, so construction work is restricted in winter. To shorten the construction period, it was necessary to use precast members for the entire building. Japan has a lot of earthquakes, so tall buildings are designed with a moment frame structure. Especially in a super high-rise building, the structure is a complex concentration of rebar as beam conjoint. A high viscosity concrete is difficult to cast inside. It's best to use full precast columns. So all columns were full precast members. In addition, beams of 2 floors and above, slabs, balconies, and corridors were made with half precast members. As a result, about 65% of concrete is precast members. So we achieved a 5-day cycle per one reference floor. If concrete was casted inside, it took about 20 days. Not to mention, the formworks of concrete members were greatly reduced. Second, hinge irrigation method for improvement of seismic performance. To avoid the damage of beam conjoint rationally, the hinge irrigation method is adapted. The plastic hinges are designed at the shifted position of the beams using high-strength rebar and mechanical joint. We did various experiments and verification, and over a long time, we use this method. We can use this method. In Japan, the design and construction may be contracted by one company. In this case, structural designer consider what the best construction method is. This shows hinge irrigation method is applied in the construction site. The precast columns and beams are simple and completely separated. Also, the extension of the beam and bars is short. Hinge irrigation method has great advantages, not only improvement of seismic performance, but also in manufacturing, transportation, and construction. Third, ultra-high strength concrete with design standard strength FC 100. In Sapporo, conventionally, we use FC 70. FC 70 is the upper limit of ordinary concrete. By solving these many problems in advance, achieves both high strength and frost resistance, even with a 2% air value, contributing to the reduction of environmental impact, and etc. in advance. We are able to use ultra-high strength concrete FC 100 in Hokkaido first time. Fourth, take-up system. Take-up is an advanced construction technology that has never been before. This system uses arch columns of the building instead of the tower crane mast. These are how take-up affect construction. No floor remains uncompleted, and we could install at any position. This project is the first step of this system. The take-up system was realized using the hinge irrigation method because the extension of the beam and bars is short. Next, a video of take-up system. It is possible to climb in about 1 hour per one floor. So the impact on the construction process is extremely small. It greatly contributed to the 5-day cycle per one floor. Finally, we will show the production drawing creation system of precast members using beam data. It saved a lot of effort in doing. That's all. Thank you for your attention. ありがとうございました。
Do we have any questions? All right. Thank you so much.
Okay, thank you.
Wonderful project. Congratulations. All right. Next, we welcome a team of presenters. Frank Sykon, Senior Superintendent with DPR Construction and one of the generous sponsors last night. Andrew Levy, Concrete Project Manager with DPR. Ash Garib, Associate with CO Architects. And Pablo Ramos, Design Engineer with KPFF. Together, they will present on the mid-rise structures category first place winner, Hope Plaza, in their talk, Rooted in the Land, Concrete as a Reflection of Place. Please help me in joining the Hope Plaza team.
Good afternoon, everyone. Thank you for being here. My name is Ash Garib. I'm with Co-Architects, and together we'll be presenting our recently finished cancer center in California. So our client is City of Hope. They are one of the top number 10 cancer centers in the nation, and they have this beautiful tradition of really putting the focus on the patients and the patient experience, and that's sort of evident even around the campus and the way that they practice. Our building is located in Duarte. It's a very mountainous sort of a climate with dry and hot, and it has very this boulder-like rocks. And the concept behind the project is sort of conceptualized as a river carving down the mountain, working its way through the site, and then consequently carving the mass of the building. What's left from that erosion are two masses that house the private functions of the building, and the void in between becomes the public sphere. Here's a view of that with how that all works out. So from the onset of the project, we always conceived the building as being part of Earth. So that was why we wanted to sort of stay with cementitious materials and earthy tones and sort of belonging to that context. So the building is essentially conceived as a jewel sitting on this earthy pedestal of concrete and cementitious materials. And we wanted it to sort of represent those kind of textures of, earth and erosion. So we used board form concrete, board form work with white cement. And this is essentially one of the first walls that we put up in the basement. The project is actually 8 stories tall with a basement at the bottom.
Seeing some of the structural presenters, and I'm not going to go as in-depth into the structural design, but there was a lot of architectural concrete, and so the primary focus will be just these 2 walls here, this one and then the one you'll see in a forthcoming slide. But Ash mentioned the concrete board form and the challenges of a 20-foot tall retaining wall. And so this one here is spanning about 40 feet. So we had to introduce an integral kind of bond beam and traditional retaining wall design. Do one-way design, but in this case we had to do a finite element analysis, find the distribution of it, and as you can see, we had to introduce an element that starts with the S. I think that word is forbidden here, but it's to cut down the span. But yeah, I mean we'll go into more detail on the next wall here.
So for the construction of this wall, a lot of the requirements, the design strength was 5,000. The actual mix, when we got it, the breaks were coming in at 7,000 psi, so we were going above and beyond the straight structural. We used type L white cement, also aggregated 3/8 and sand. We worked on mock-ups to make sure that we were able to achieve that color and the board form look. And then we had to get formwork designed, especially with the radius too. There was a lot of bulkheads, strong backs, shoring towers, and especially with that bond beam, it was so congested, we had to get pockets in order to fit the hose.
So as the patients essentially walk through that public sphere that we showed, there is an area of the building where we carved out, and it's essentially, we call it the sunken garden. So it's a void that kind of connects the exterior and the interior together. And it's also has this sort of a ribbon spiral that kind of wraps itself around the building. Probably.
Yeah.
So this here, is a kind of unique design. When you have a large spanning retaining wall, usually, you have to make it really thick and a lot of reinforcement. In this case, we utilize the geometry of the wall itself and not have to introduce intermediate support. So we kind of saw it as a sideways or horizontal truss, or horizontal arc, which we essentially modeled kind of as again, like I mentioned earlier, with the finite element analysis, so that we can make this work without having to introduce any intermediate supports to really achieve the vision of the kind of sunken garden look. So.
Frank, you want to talk about that?
So I think one of the reasons why we're probably all in this industry is because, we like the friendships that we build on projects. So City of Hope as a cancer research institution has a great story, but also the project team, where people come together early on in the project before you deliver goods and the architectural wall. You're designing and doing structure well in advance of, opening the building. So I love the snow in Aikido, because in California, I don't know if you guys have ever heard about this, but we have atmospheric rivers now. So we used to get a fraction of an inch and it wouldn't rain for 11 and a half months. So this right here, we decided this is a great, the sunken garden, affectionately called. This is where we placed our tower crane. So the Pablo will work out the structural design for the tower crane. We're about 2 days away from pouring that tower crane foundation, and we got 14 inches of rain in 3 days, which is more than LA gets an entire year. So we're about this deep in water, and we got to do it again. So I love the backstory, because that's really what makes the project and all these friendships come alive.
You want to talk about how congested all that?
Oh yes. Again, this is the sunken garden, affectionately known, but we did all our shoring outside of the garden so we could do this complex geometry, and then this is also where we did our tower crane foundation.
This is essentially the finished product with the board form wall, and you can kind of see the ribbon going around and how the guardrail wraps around it. In addition to the board form walls, we also have sort of a variety of finishes and different ways of going about the concrete. So Andrew, maybe you want to, or Frank, maybe you want to kind of talk about all the mock-ups that we did and the different finishes that we're using.
Yeah. So for our white concrete that we did, the white cement, we essentially went through the similar process. We had multiple meetings, distinguishing features, what's important, how are we going to achieve this, and I think if you go to the next slide, there's another example. But but if we had prefabricated forms, and we figured out how we have to do that and where we come from. Next slide as well. Same thing, precast benches. Everything was so detailed and so out in front that we had time to make any adjustments and make sure that when we're building it in the field, it matches with architect's vision and works with structural design. We did a great job with all of them on this by identifying those.
And again, just a little bit behind the scenes, you see all the courtyards and the decorative concrete. We're actually on top of about 4 or 5 feet of high-density concrete, because this is a medical facility. So there's a linear accelerator in the basement that will shield all the radiation. So all that needs to be coordinated in advance, because this is actually the basement, it's waterproof, and then there's a lot of modalities for the hospital underneath there.
And we also, did as many mock-ups as we could, trying to get things right. And it always becomes apparent that the first try is a little, it could always use improvement. So having a great team that, is willing to kind of make sure that things are right and not just on schedule, on budget, I think really helps to kind of bring a project of this magnitude together. So thank you all for your attention today. Appreciate you.
Any questions for the team? Roger, thank you, gentlemen. Yep. Well done, well done. All right, our 8th presentation will be given by Shia, Chairman of Yu Construction. Gia has 27 years engineering experience, holds a BS and MS degree in civil engineering from National Taiwan University and is a licensed professional engineer. Yu has repeatedly earned Taiwan's highest national honors for quality, safety, and sustainability. In 2025, as general contractor for the National Taiwan University's Humanities Hall, he received Taiwan's first ACI Excellent Construction Award, underscoring Chairman Chia's engineering rigor, sustainability, innovation, and global vision. We will be presenting on the mid-rise structures category second place winner, National Taiwan University Humanities Hall. Please join me in welcoming
Good afternoon, ACI members and friends. Congratulations to all the winners. Mr. Price, thank you for your help. Mr. Rusty, thank you. Yeah. Fengyu is a construction company from Taiwan. Now that's me present at National Taiwan Humanity Hall on how to boost concrete performance. There are 23 million people in Taiwan, with 2 meter of concrete consumed per capita each year. Concrete technology and its applications are well developed in Taiwan. Taiwan ranks 22nd among global economies in terms of GPT, with 70% international market share in wire foundry. As a high seismic region, Taiwan relies on high-performance concrete to support both semiconductor industry and the everyday infrastructure. TCI has been leading the advancement of concrete technology in Taiwan, with a focus on decarbonization and circularity. It's an honor that two Taiwan projects won ACI Excellence in Concrete Construction Awards in 2025. National Taiwan University Humanities Hall stands as an emblem alongside its iconic heritage main gate, College of Liberal Arts, and the Royal Palm Boulevard. Concrete interprets the existing courtyard house, forming modern quadrangle that bridge heritage, campus, and the city. The 50-meter steel truss, supported by monumental concrete columns, span over the second courtyard, offering an unobstructed view of historical architecture. Concrete shear walls enhance the hall's seismic performance by 50%. The steel truss is filled with high flows, self-compacting concrete to improve fire resistance, corrosion protection, durability, and seismic performance. To control cracking, we adopt a 4-stage concrete mix design, refined by on-site markup to finalize the optimal mixture. By integrating BIM technology, the entire structure was deployed into 117 concrete pouring units. For the 50-meter-long steel truss, a post-cast segment method was used. 3 main segments were cast, each cured for 28 days before placing a 60 cm wide post-cast strip. This released 28% of the concrete shrinkage stress, effectively preventing crack. Various architectural details show the workability and the versatility of concrete. National Taiwan University Humanities Hall is shaped fair-faced concrete cast with cedar formwork. The natural grain, animated by light and shadow, convey a quite wide resonance with the building's humanistic spirit and bridge the dialogue between past and present. Sustainability strategies, low water cement ratio to reduce cement content, dredge-driven aggregate to reduce coiling, 30% cement replacement with GGBS, fair-faced concrete as a final finish to eliminate secondary surface treatments, precast UHPC sunshade to reduce thermal load. Thank you, Taiwan team member. Stand up, please. Yeah. So, give a biggest, give a hand. Thank you. But I have a video. See. Yeah. Video is okay.
National Taiwan University Humanities Hall is surrounded by a century-old historical campus. Concrete reinterprets the former courtyard house, forming a modern quadrangle that bridges heritage, campus, and city. The 50-meter sky bridge, supported by monumental concrete volume, spans over the sunken courtyard, offering an unobstructed view of historic architecture. Concrete shear walls doubles the structure's seismic resistance. Steel frameworks of the sky bridge are enhanced with HPC, ensuring fire resistance and corrosion protection. No coatings, no additional finishes. SCC is cast with cedar frameworks that imprint the surfaces with wood grain for a soft and warm appearance. Mock-ups and testings are done to evaluate and refine the mixture, techniques, and aesthetics, while BIM assists in achieving accurate execution. Various architectural details show the workability and versatility of concrete. Sustainability begins with how we mix the concrete. Dredged river aggregate replaces quarried stones. Slag instead of cement, reducing carbon emissions by 2 million kilograms. A low water binder ratio enhances durability and serviceability. Precast UHPC sunshades at 3 angles efficiently lower heat loads. Each concrete pour is a firm commitment. No haste, no compromise in concrete and in the human spirit. Fengyu Group.
Today is my birthday. My first time in the United States. It's my honor to stay here and give a presentation. Thank you.
Good birthday, Mom. All right. So in our next presentation, we'll welcome Wei Liang, project manager for the T3 project at Taiwan Toyon International Airport and assistant vice president at CPCI. They'll present on the apron project covering 420,000 square meters at Toyon International Airport, the second place winner in the flat zone category. Please join me in welcoming Mr. Yang.
Hello, everyone. My name is David Ling. I'm very happy to represent Taoyuan International Airport Corporation to introduce everyone this mega project. As you know, in this year we win the award is about apron and taxiway. It's one of the tender package of this mega project. Total, we got 25 tender package for the whole project and plan. So I joined this project since from 15 years ago. Willie is 12 years ago. So we worked together a long time enough. So, in organization with this slide, TYLIN, WSP, and NACO will be the planner and the project management team. And CCI, Rachel Rogers, ARAP, and the FCA is design and supervisor team. And for TP3 is this apron project. BES is the contractor which build the apron and taxiway pavement. Okay, I will hand over my microphone to Willie, and he will keep going for technical presentation.
Okay. Before the presentation, I would like to thank to ACI for giving this opportunity for us to learn a lot, so many great concrete projects from all over the world. Okay. My name is Willie Young, project manager for design and supervision consult of Terminal 3 project in Taiwan Taoyuan International Airport. It's a huge project area, and also it is demanding for us. We are so proud of our achievement, not only for the huge area, but also the work involves so much detail and require a lot of monitoring coordination. And we did it without any interrupting the airport operation. Yeah. Here's the contents of the presentation. This aircon construction located in Taiwan main gateway, Taoyuan International Airport. This airport is the number 30 business airport in the world for handling of passengers. Currently, new mega terminal is being built to accommodate the future growth and air traffic in Taoyuan Airport. And this project is going to provide additional apron and the taxiway to provide 27 new contact stands. Therefore, the content of this project includes the surface area of 42 hectares of rigid pavement, 30,000 concrete slabs. Each slab is around 5 by 5 meters. And also the volume of the fractured concrete is 165,000 cubic meters. Structured concrete, 94,000 cubic meters. Let me introduce the future of this project with some slides. Optimal design. We adopt the FAA standards for determining the pavement thickness and to accommodate the varied types of aircraft and the volume of operation. Then the PCC surface layer has a bending strength 700 psi and 46 centimeters thickness. The layer below the surface layer is cement treatment grade bottom layer. Thickness is 30 centimeters. These are all the design to improve the durability and resistance to water damage. The second feature, saving on cost and reducing carbon emission. The total volume of concrete in this project is around 260,000 cubic meters. And considerable amount, that's 48,000 tons of cement is replaced with reusable resources like polyolenic material, which can improve the constructability and the durability. And overall, we also reduce the carbon 700 tons of carbon dioxide. Okay, that's the material. The second feature, applying special tools and the technology, we developed a testing machine to conduct a heavy-duty vehicle test of the pavement. This is based on the FAA's spec. For the large area in April, we also adopt a leader technology to apply the ground data and the analysis to confirm the flatness of the entire area, April area. It's an efficient and comprehensive way to do that for inspecting large area. Precise measurement and control. We constructed 30,000 slabs in a meticulous way, which includes using steel molds. This steel molds and set the elevation of four corners of each slab. Therefore, we can control the overall slope for drainage. Soil cutting and pouring is also performed with precise steps on site to control cracking. This is some figure here. In order answering, besides the precision, in order answering the specific kind of condition in every area, we apply the curing agent to create a tough and durable water retaining layer to slow down the water loss. It's an effective way to ensure the quality of pavement. Okay, here is a short video to show the critical water at the site. This is the heavy vehicle testing. And the leader technology to be used to confirm the flatness of the apron. 5x5 slab. Put the steel mold to and this over all this data is a design data. Therefore, we can have the overall flat area, down bar, and tiny bar. This is the PCC pouring. Roller paving and the leveling. Sweeping with the pavement to increase the friction. Okay, we're spraying the curing agent to prevent the water loss. So cutting. With the elastic. Okay. Then let's quickly go through some features of this project. Okay, we have a rich pavement in huge area that's 42 hectares. And we complete the additional parking gates that 27 to provide more capacity for the growth traffic. 13,000 concrete steps skillfully joined together without defects. And superimposed pavement structure that to increase the strength and improve the durability. Flat surface for aircraft movement and drainage that results from the meticulous construction way for the stack. Huge volume of concrete to accommodate the different loading from the different, because we do have the focus the different flight in the future. Then we know, because the loading is so heavy for the aircraft and only such small area, then the loading is totally different from the vehicle. Yeah. Okay, we also have 220 worker to reserve for the other project, the environmental way to do it. Okay, besides the good condition of the effort, there is something more exciting on the way, because the condos, the terminal building is going to open in the coming future. Yes, and we Taiwan is eager to show its fantastic achievement at that time. That's my presentation. Thank you.
Any questions for Willie or Willie?
That was just the apron area, right? That was not any runways? No, taxiway also included. Taxiway, not no runway. Okay. Yeah.
And it looks like we have the winning project for next year. I hope so.
First place.
Good luck.
Yeah.
Very good. Very good.
Thank you.
Thank you so much.
Thank you.
Coming after 3 years, 4 years. Yes.
I appreciate that. All right. Our final presentation today. Joe Kersley, professional engineer, structural engineering, senior principal at CKC Structural Engineers. Joe's also a voting member for numerous committees and associate member for the joint ACI, ASC, and Restress Concrete Committee. Joe will present on top of the mayor, meeting the challenges of tall building design, which won second place in the higher-rise structures category. Please welcome Joe.
Well, thank you, Rusty and Denisha, for putting this whole thing. And I would like to extend my thanks to the entire ACI staff that put that ACI Excellence Award program together. It's humbling and gratifying to be part of it. We started placing our project in this program since the inception. We already won 4 times high-rise category, second place, yet to win the first place. But it's a great thing about this award. It's actually an international award. When you come to these presentations, as we can see here, you have people from all over the world bringing these beautiful projects. As we saw last night, all these entries were amazing and a lot of hard work. Every project is touched by 1,000 people or more by the time you design it, construct it, build it, and it changes the landscape of cities, for that matter, and touch us in so many ways. So the air is a long history. It's in Seattle. If people don't know, Seattle is a high seismic region. There's a subduction plate moving. A lot of attention is given to earthquakes. High-rise buildings are particularly complex structure to design in high seismic areas. The air in particular is a 45-story tower, 5 levels below grade, multifamily high-end luxury condominium in the Denny Triangle, which is kind of ties in downtown. It's a vibrant neighborhood of Seattle that ties in downtown with South Lake Union, if you guys have been to Seattle. And we had to pay critical attention to cost. It's a private-driven project, and to speed, because schedule, cost, all these things come together to make these projects happen. So just a quick overview. It's 454 units. It's about 600,000 square feet, 6 levels below grade, and of parking, and then 3 levels above grade was parking. Beautiful lobby area was amenity that ties in the corner of that street. Many thanks to the developer Holden Partner Group. The good thing about them, they're also the general contractor. Holland Construction will also thank the concrete contractor, which is Conco Concrete, and Robert Thompson with the architect. If you could see, look at the building, the way it's been designed, it actually was inspired by the Pacific Northwest, where you have these jagged sides. This is actually the tectonic plates, quote unquote, per the architect, that kind of shows that facade that goes in and out, which created some challenges for us on a structural standpoint because we had to create these long cantilevers without moving columns. Quick thing on the structural overview of the building, has a lot of great things and innovations and buildable details throughout. So we use 8-inch post-tension slabs. We have spans about 29 to 30 feet and cantilevers up to 12 feet without any drop heads. We use high-strength column up to 15,000 PSI. That was a bit challenging because the entire building will also use one of the first buildings that used Type 1L cement in the U.S. of that size to reduce carbon footprint. We're also on the walls, so the lateral system of the building is actually not allowed by the prescriptive language of the code, so we have to do performance-based design. So we have to analyze the building with this core, and we'll put fiber link beam that are not part of the code, but you can do it if you do nonlinear analysis and show that the performance of that core would work nicely. It takes a lot of energy. You put 11 pairs of ground motion. Each one is about a minute long, and every 0.05 seconds, you check the stresses on the building as the 11 pairs moves that model. So it takes a lot of iteration, a lot of back and forth. One of the things we wanted to do is we had 16 columns. We worked hard and fought hard and negotiated location with the architect and the ownership so we don't have to add any transfer beams. Buildings this size, a transfer beam would be a floor height and would slow down construction and would disrupt the behavior of the lateral system. So here's a model. This is out of Revit, which is Visicon 2, but you can see here the middle, the red is the core, going concentric core from the foundations, the foundation mat, all the way to the roof. You have 16 columns around. We created some crafty, you could see here, jogging and walking of columns. Some of them walked in 3 different directions, just so that we don't put any transfer beams. So we didn't have any transfer beams at all from dynamic base. We call it dynamic base, which is grade level all the way to the top, which made the things much easier, less congestion, and eliminated all the transfer beam that could impair some of the occupancy of floors. One of the cool things we did, and this is supposed to be a video, maybe the next click should do it, is because we had a high strength, you can see here, this is the column, and the column was 15,000 PSI concrete, and the slab was 6,000 PSI concrete. So we don't have, the code requires you to do puddling. I don't know if you guys know puddling. You basically take another mix of concrete, you put it on top of the column to intermix, and then because you don't have so much differential between the slab mix and the column mix, add the column slab sandwich, which is right here. I'm going to click to see if that video will work. Oh yeah, it does. So these are the stud rails. This is a rebar, and the way we do that, these are the shear bars that we put into this. The green is the PT cables. You can see them here too. And then this is a top reinforcement, and then you put this stay form, and then when they pour the slab and they stress it, you have this little hole because that stay form keeps the core of the column without being poured, but it does not slow construction because you pour the slab, you stress, you have this little cavity over the column. The next day they come and pour the column, and the concrete mix of the column goes into that cavity. It's a pretty cool, slick trick. I'm gonna replay it again, see if that works. So you could see it again, and then avoids the puddling. The trick was usually to put the stay form, but what they did here, they put that stay form first. You have to make sure you put the shear steel bars so that on top of the friction between the concrete, you have shear steel that passes to, it's like a midpoint bar that goes into that joint. And then they put stay form again up here after they put the top bars, and they pour it. Much easier than putting 2 mixes, try to intermix them, so on and so forth. So that was a big thing on constructability and buildability. The other cool thing on that job is we used actually fibers link beam. High dosage of fiber, you could see it, and instead of using the diagonal reinforcement in these beams because they are taxed by a lot of shear, and a regular beam does not work. So what we did here, we put basically that piece of concrete between the two walls. So this is a boundary element of the wall, and this is the other boundary. Between the two walls, we put a special mix with high fibers. It's about 160 pounds of fiber per cubic yard. It's a very healthy fiber dosage, to 200, depending what we need. But what happens is you reduce the rebar in that beam by about 40% from a typical beam. So it's much easier to place. You don't have the diagonal that clashes with the top rebar coming down. So it turns out to be a very constructible tool that streamlines the rebar of the core going up the building. And the neat thing about it, a lot of times you can pour this after the fact. What they do is they pump the wall with concrete, they bucket this was a steep bucket with fiber concrete, they vibrate it, and they put stay foam, and they keep on going with the building. Here's a video showing how that fiber concrete is putting in. It's interesting, we use the SCC mix. When you put the fibers, not because the fibers suck, steel fibers, they don't suck water, but it turns the SCC mix to a 6-inch slump. You have a 27-inch slump for a self-consolidated mix, and you put these fibers in, suddenly you're down to 6 inches, plus or minus. So, but they all over the mix, you don't see them when you strip, so it's a pretty neat thing. We've done about 15 buildings like this throughout. Now, the underground, the below-grade construction was really interesting. First of all, we start with the mat. We had a lot of cool concrete specification for different concrete mixes for the building, but the mat is basically about 10 feet thick to plus 10. Around the elevator pit is about 15, but basically most of it is about 10 foot thick. And they did a single pour for the entire mat, about 5,000 yards. So basically, they start at night, they finish in the morning, about 12, 14-hour pour. You have trucks coming in. So think about it, 10 feet of concrete, it's mass concrete. There's a high heat of hydration, so we always make sure that the cement content of these mixes is less than 450 pounds, and we kind of extend the strengths, so you don't need that strength till about 90 days or 120 days to make it easy on the ready-mix guys to bring those mixes to us. If you pour that mix like a regular 6,000 mix with 600-pound cement, you won't be able to walk on it in 2 days. It's going to be very hot. So that's one. Two is we cover it so we keep the heat differential the same between the center and the top of the mat for a few days till things come down. We'll look at the temperature gauges for that. The other cool thing is it's a pencil tower in the downtown, so it's 120 feet by 100 plus feet, 110 feet. So you want to go fast, and the basement wall creates a trouble because if you have to pour the basement wall, pour the slab, pour the core, you'll be stuck in that hole 6 levels below grade for several months. One job we did, they were in the hole, they came to go down and up, took them a year. So what we do is this is actually the shoring system, that's not concrete. We allow them to put the slabs against the shoring system, and then what they do is they detension, there's tiebacks on the shoring system, they detention it, now the slab becomes bracing the shoring system, not the tiebacks, so you don't have to do blockouts in the basement wall. And then you don't do the basement wall till later, so these are formwork put at the joint of the basement walls. You have a basement wall above, basement wall below, slab in, and what they do is they come back later when the tower is up to level 2, they come back and shoot with shotcrete the basement walls. And they're pretty thick basement walls, 16 inches. And then, so embodied carbon was an interesting thing on this. Let me just go back here too. One of the things we used is we used a grade 80 steel throughout the foundation, grade 80 steel throughout the boundary elements of the core walls because there's a lot of tension involved. And then we used the confining steel, was grade 80 steel to reduce the amount of confinement. The other thing we did is we created these column cages to lift, so you reduce the amount of times you put these columns on site. So that if you have 16 columns, what they did, they staggered the columns. It's a cage that goes 2 levels. So some of the columns, you only have to place half of the column every cycle of floors because the other one is already sticking up we do with the next one. So it's 2-story lifts. And that works really nicely and speeds up the floor cycles by quite a bit on the typical floors above in the building. The carbon was interesting because by just using Type 1L cement, we were able to reduce about 10%. So this is about equivalent, we did the math on it, about 450 tons of CO2 reduced just right off the bat. And then being efficient and putting transfer beam and all that stuff, people don't realize a lot of the carbon reduction is the big question, and I always ask myself, it's like, you see all these highways, a lot of these bridges, but you can easily reduce carbon by making your design a bit more efficient by at least 10%. You always can make your design a bit efficient. So that was a big thing, and then so high-strength bars also reduce the embodied carbon. Now, depending how steel is being made, either from iron ore or recycled steel, most of the stuff we use in the Northwest is recyclable steel, so there isn't a lot of CO2, but there's still some, because you have to heat it, melt it, and transport it. So by using high-strength steel, you reduce the amount of rebar you use, and then therefore that helps with the carbon footprint. So the project here did it great. We won a couple of years ago the NAIOP High-Rise Residential Development of the Year in 2024. Last week, we won the NCSCA, which is the National Council of Structural Engineering Associates. It was a summit in New York. We won the Outstanding Multifamily High-Rise Project category for 2025, and a few other awards and publications. And then CRSI Award right here in 2024. And yesterday, we won the ACI Excellence Award, second place, but we're working on the first place. And so basically, conclusions, we are advancing material. We use innovative material like fiber link beams, fiber and concrete, leading edge constructability. I showed you that detail. And all of it happened was a collaboration with the concrete subs and the ready-mix guys. We sit down with them early on, and we try to make them comfortable with the ready mixes. Otherwise, they get freaked out when they see a 15,000 PSI mix. And I think that's it. Any questions?
15,000 PSI with 1 ounce of any questions for Joe?
Yeah, we did quite a bit of mock-ups early on. We used the first mix. I mean, this is not the first building we used fiber, but we reduced the fiber here a little bit different. But you have to do mock-ups. And what we found out, if they use the SCC mix, you add the fibers in it. The key is how intermix the fibers. You have to do them in the plant early on. You have to talk, because the ready-mix guys don't like to put other stuff than what they have in the concrete when there, but the fibers have to be intermixed so they disperse quite nicely. So we have a lot of specs on that and how to deal with it because we did a bunch of samples on that.
Very good. Thank you, Joe. Thank you. Congratulations. Yep. All right. I want to thank everyone for attending and celebrating the winners here. We hope you enjoyed taking a closer look at these remarkable concrete projects. Again, if you missed any of the projects, be sure to watch the videos on the ACI Excellence website. Those are all posted. And if any of our speakers have a few more minutes to invite them to answer questions after the session. Again, I want to thank everyone for attending and again, celebrating all these great projects from around the world. Thank you so much. Denise has got